Alrighty, so this is the example that the professor gave to us on Thursday, and it originally comes from PS6, problem number 8. This is the information that you're given. You're given the mass flow rate, you're given T1 and then P1, and you're given P2, and you're given the molar specific heat of ethylene oxide, and you're also given the compressor efficiency. So over here we have it written down. I drew out the compressor. Stream 1, you have mass flow rate, T1, P1. For stream 2, all you have is the pressure. You're also given the efficiency of the compressor here, 0.75. And you need to find the work. You need to find the actual work required by the compressor. Okay, and over here I wrote down the specific heat for ethylene oxide. Okay, so ultimately what you need to find is the actual work required. You're going to use this formula. Efficiency of the compressor is isentropic work over actual work. Rearrange it to find actual work. You already know the efficiency, so in order to find actual work, you're going to have to find the isentropic work. Okay, and notice that because your specific heat is given in terms of molar units, you're going to have to convert your mass flow rate into a molar flow rate. So in order to do that, you're going to need the molar mass of ethylene oxide. If you do a simple Google search for ethylene oxide, it will tell you over here, it'll tell you that the molar mass is 44 grams per mole. That is equivalent to 44 kilograms per kilomole or 44 pounds per pounds mole. The value stays the same, and you can change the units according to what you need, right? And also, a little bit of information here tells you that ethylene oxide is a flammable, colorless gas. It is a gas, okay? So that's kind of important to know, that it is a gas. It is a gas at low pressure. P1, 1 atmosphere, is low pressure. So we can say that this is an ideal gas. And that's important because that lets us know which formula to use to find the work, right? Okay. Over here, I'm just showing you converting from mass flow rate to molar flow rate. You want to divide by molar mass. That gives you 0.0227 pound mole per minute. Okay. If you try to do an energy balance, an isentropic energy balance, you'll come up with this. Isentropic work equal to the molar flow rate times H1 minus H2 isen. The problem is we don't have, for ethylene oxide, we don't have any tables or diagrams that tells us the enthalpy values. So what we need to do is use this formula, right? And this just comes from our notes. I also have it written over here. So the change in enthalpy, right, is the integral from T1 to T2, Cp dt. Okay, in our case, it's going to be from T2 isen to T1, right? That just reflects this Cp dt. Okay, but in order to do that, in order to find isentropic work, we first need to find the T2 isentropic, the isentropic temperature at stream 2, right? Okay. So these are just, this is the formula to find change in entropy, right? In our case, because we're looking for isentropic work. Isentropic means that the change in entropy equals 0. So we're going to have to set this equal to 0, right? Okay. So this formula set equal to 0. We need to apply it to our problem. So I just have it written here. Okay. So this was the Cp divided by the T minus the gas constant, P1 over P2, natural log of P1 over P2. Okay, make sure that your units match up. We use these, the gas constant 1.987 BT per pound mole degrees Rankine, because that matches up with our units here. That's important, right? So I'm just showing you how to evaluate it over here. Okay, you're evaluating from 530. This was T1, so it was 70 plus 460 gives you 530 degrees Rankine. You need to find T2 Isen. Okay, so here I have it written out. It is not algebraically feasible to find T2 Isen, so there really is no easy way to do this algebraically. What you need to do is find it by trial and error. You just have to like give different values for T2 Isen until you get a value of 0 for your entropy change, right? So what we will do is we will use some software. I use Google Spreadsheets. You can also do the same thing on Excel, but for me it was easier to use Google Spreadsheets. And there's a goal seeker application that helps you do this. So over here, I'm going to X that out for now. I already did it over here, but I'll do it again just to show you the steps. Okay, so your alpha value for specific heat was 10.03. Your beta value for specific heat was 0.0184. Your T1 was 530 degrees Rankine. T2 Isen, we do not know. That's the thing we're trying to find. But we cannot leave it blank. We must put something there because it's going to be part of our algorithm. And if we leave it blank, you're going to get an error. So you just need some sort of placeholder for now. So I'm going to use 10. You don't want to put 0 because if you put 0, you're going to end up with, you know, a 0 in the denominator. That's not going to be good. It's going to come back as an error. You also don't want to put 1 because if you had ln of 1, that'll give you 0. So you don't want that either. So I chose 10 arbitrarily. You can choose any kind of number, you know, any positive value greater than 1. But I use 10. I think 10 is a good number to start with. Okay, so P1, it was 1 atmosphere, which is equal to 14.7 pounds per square inch. P2 was 250 psia, pounds per square inch. Your gas constant, we use the value 1.987 BTUs per pound mole degrees Rankine. And your difference in entropy, your entropy change, right? This is going to be a formula. So we do equal sign. So the program knows that this is going to be a formula. Alpha times natural log of T1 over T2 Isen, close that, plus the beta value times T1 minus T2, close that, okay, minus the gas constant times natural log of P1 over P2, close that, hit enter. Okay, so if the T2 Isen was 10 degrees Rankine, then your entropy change would be 55 BTUs over pound mole degrees Rankine. That's not what you want. You want your entropy change to be 0 to reflect the fact that it is isentropic. So what we're going to do now, I'm going to show you how to use goal seek. You go over to add-ons, and if you don't already have it downloaded in your program, you would just go to document add-ons and type it in and follow those steps. I already have it downloaded, so I'm going to go over here. I'm going to open it. Okay, so we want to set the value for entropy change, which is this value, Q12. We want to set Q12 to 0, right? Because it's isentropic. The difference in entropy is 0. By changing the T2 isen value, which is this one, Q6, right? Q6. Okay. Hit solve. And it's going to go through, it's going to run through a bunch of different numbers until, oh no, that's not the one. Okay. It should have been Q5, sorry. Q5. I don't know what this is. Okay. Q5. Okay, solve. Okay, it's running through a bunch of numbers. It's performing a trial and error method to find a value. Okay. So it's not exactly 0, but it's very close. So the T2 isen value is approximately 691.22 degrees Rankine. That is approximately the value of T2 isen that will give you an entropy change of 0. So go back to our work, and I have it written here. It's 691.22 degrees Rankine. If you subtract 460, it gives you degrees Fahrenheit. We want to use degrees Rankine for the rest of the problem because, you know, when you use the formulas, you want to use absolute temperature. Okay, so we go back to this, to the formula for isentropic work. Okay, molar flow rate times the integral. These are going to be evaluated in degrees Rankine. Okay, this is your CPDT. This I just wrote the units here. This is going to be BTU over pound mole degrees R. So I'm evaluating that. Okay, taking the antiderivative and evaluating it, and I end up with negative 77.83 BTUs per minute. Now, okay, so all we got to do is go back to this formula again, rearrange it to find our actual work. That gives us negative 103.77 BTUs per minute. That's the actual work required for the compressor. And if you want to convert that to horsepower, you would multiply it by 60, divide by 2545. These are the conversion factors. And it would give you negative 2.4465 horsepower. Okay, I hope that was helpful.